In this video, we are going to be addressing the issue of multiple electric fields and magnetic fields having an effect on a charge. We have this region over here where we have two parallel plates crisscrossed with another set of parallel plates, generating electric fields as shown. The blue plates are projecting an electric field upward of strength 1,000 newtons per coulomb. The red electric field is crisscrossing to the right, and that electric field has strength of 300,000 newtons per coulomb. Into this electric field, we place a positive particle. The particle has a charge of 67 nanocoulombs, and it has a mass of 6.5 grams. My question for you is, what magnitude and direction of magnetic field needs to be projected into the region such that the particle will remain stationary? Begin solving, and I will explain the answer when you resume the video. All right, to address the first issue, that was a trick question. If a particle is stationary, there is no force generated by a magnetic field. If you recall, the formula for a magnetic field, FB, is charge, velocity, magnetic field. If the particle is stationary, the velocity is 0, and thus the force is 0. So you cannot have a magnetic field cause the particle to become stationary. So, aside from that being a trick question, let's ask the actual question. The particle is shown to have a velocity now of 127 meters per second into the page. What direction and strength of magnetic field is necessary such that the particle will pass through this region undeflected? When you're ready for the answer, resume the video. Now, for those of you just interested in the right answer, the magnetic field magnitude is 7,839 Teslas, directed at 72.47 degrees below the negative x-axis. If you did not get that answer, go ahead and recheck your work. If you didn't get the answer and you're really stumped, I'm about to go through the actual problem and how to solve it. Resume the video when you are ready. Okay, as always, to begin a problem such as this, you need to make a free body diagram. Here is my particle. It is just hovering in space. There are three forces acting on the particle. We have gravity in the down direction. We have an electric force to the right, and an electric force up. How do we know that is the direction of the forces? Remember that electric field lines always point from positive to negative, which means that this plate down here at the bottom has to be positive, and this plate over here on the left has to be positive. Since our charge is positive, it's going to want to move away from those plates or be repelled from them. All right, remember that our formula for force caused by an electric field is QE, and in this case it's QE, in this case it's also QE. Remember, those E's are different because they are different electric fields. So we have to find a magnetic field that will cancel out all these forces. So first we have to sum all the forces. Well, let's start by summing our forces in the Y direction. Sum of forces in the Y. All of our forces in the Y direction is QE up Q E up, so that's positive, minus mg. Okay, so that means that sum of forces in the y equals 67 e to the negative 9th, because that is nanocoulombs, times 1,000, minus our mass, which just so happens to be in grams, and we need the mass to be in kilograms. So 6.5 grams is 0.0065 kilograms times not negative. 9.8 is g. So our sum of forces in the y direction ends up being 0.06363 newtons, or thereabouts. So let's look at our sum of forces in the x direction. Sum of forces in the x direction is simply QE for this situation, QE. Okay, so sum of forces in the x direction is going to be 67 e to the negative 9th times the second electric field, which is 300,000. So sum of forces in the x is going to be 0.0201 newtons. So now let's rewrite our free body diagram with just the x and the y forces. Here's my charged particle, and we have a force this direction of 0.201. Oopsie, that is not right at all. Erase. 0.0201 newtons. And then this Fy, that is, and actually is negative, indicating that it is in the downward direction, because as it turns out, gravity is bigger than the electric force. So it is a downward force of 0.06363 newtons. So now we've got down to two forces. We had three forces, now we have it down to two forces. And I think should be pretty obvious that if it's being pushed down and to the right, that the resulting total net force is going to be something like this. Down and to the right is our resultant force. So how do we combine two forces at right angles? We apply the Pythagorean theorem, and we know that our resultant is going to be equal to our force in the x squared plus our force in the y squared, square rooted. Because if you rearrange this, you can rearrange this to be, here's my dot, you have a force of 0.0201 this direction. And if you do tip to tail, you have force down of 0.06363. And our resulting force is the hypotenuse formed by that triangle. Okay, so we can do the Pythagorean theorem to get the hypotenuse, which is what we're doing right here. And as it turns out, when you do the resulting force is 0.0667 newtons. So all three of those forces added together give you a resulting force of 0.06 newtons. At some angle, because we're worried about the direction, we need this angle in here. Well, if we want this angle, we can do tangent. Tangent will be opposite. Tangent of theta is going to be the opposite, which is 0.06363 over 0.0201. Theta equals tangent to the negative 1 of this. Let's not rewrite it. Gives a little more space here. Theta ends up equaling approximately 17 0.53 degrees. So we have a direction and a force for all three of these charges combined. And that's just telling us the situation as it stands. We have a particle. We'll redraw this with simply the one force on it, the one resultant force. So we have a particle, our green particle of excitement, and it's sitting here. Here's my x-axis. Here's my y-axis. And we know that there's a resulting force this direction of 0.0667 newtons, and we know that there's an angle in here of 17.53 degrees. Well, we want to come back to the question, because this happens often in physics, where you do all this work and you forget what the question is. The question was, what magnetic field do we need to project to make the particle move undeflected? Well, right now, the forces are trying to push it down to the right. So if we want it to be undeflected, we need a magnetic force that will cancel this force that's pushing it down to the right. So our magnetic force has to be up to the left. That's our FB right there. FB has to be up to the right. Okay, and the angle it'll form right in here is also 17.53 degrees. And that's the magnetic force. That's the magnetic force. So now we know that these two forces have to be equal in magnitude in order to cancel each other out. So can we get the magnetic field from that? Well, FB equals QVB. We know that it has to equal 0.0667, and that has to equal our charge, which is 67 e to the negative 9, times our velocity of 127, times our mystery b. So when you solve it out, our magnetic field needs to be a strength of 7.839 teslas. So thus we have gotten the magnitude of our magnetic field. If you apply your right-hand rule to this, remember that the magnetic field needs to be perpendicular to the force and perpendicular to the motion. The motion is into the page, so it's got an X motion, and the force is in this direction. So therefore, the magnetic field has to be this direction, perpendicular to both. That's the only direction it can be, perpendicular to both. So we recall here that this whole angle here between these two, in order for it to be perpendicular, that has to be 90 degrees. So, and we know this part right here is 17.53 degrees. So theta equals 90 minus 17.53 degrees equals 72.47 degrees. And we have to specify what direction. Below the negative x-axis. Thus we have solved the problem. It looks like a lot of work, because it was, and thus we've solved this problem. If you have any other questions, post them in the comment section. If I made a mistake, definitely post it in the comment section, and I will make a correction as needed. Thank you.